Hey, thanks everyone. Welcome to my talk. It's going to be on heap exploitation. I'm going to be talking about building your own heap allocator, some of the inherent vulnerabilities that come along with implementing an allocator, and how to exploit them. Just a little bit about myself. My name is Kevin Massey. I am a security analyst. I do some independent security research in my free time. You can find me on Blue Sky, Hype, Blue Sky, and on Twitter at ScratchAdams118. You can also look at my GitHub if you want. All of the code that I'll be talking about in this talk is on my GitHub, and I will link to that as well as other resources later in the talk. All right, so what is the heap? So essentially, the heap is an area of memory used by a process for dynamic allocation at runtime. So what we mean by that is when a process is handling memory and allocating memory, it either knows how much it needs to allocate or it doesn't. So when it doesn't, it has to do this dynamically. So for example, if you're working with an image processing program and you get an image from a user, you don't know how much memory you're going to need until that user gives you that image. Heap memory can also be accessed globally throughout your process. So in contrast to stack memory or to local variables, which might be only accessible to the function, heap memory can be accessed pretty much by any function within your process. The allocator itself provides a layer between the process and the OS kernel to manage request and return memory. And there's also different types of heap management strategies. So there's free list based, there's BIBOP, which is big bag of pages, there's separated metadata, and there's inline metadata. The allocator that we'll be talking about, or the implementations that we'll be talking about, are free list based and they're inline metadata. Some examples of existing heap allocators. PT malloc 2 is the big one. This is the glibc, which is the GNU standard library implementation. So if you've written a program in C or C++ on Linux, this is the allocator that you will be interfacing with when you call malloc or new. Another example is JE-malloc. You'll see that used in the BSDs, specifically FreeBSD. It's used in Firefox. It's used on Android. Partition alloc is the general purpose allocator that they use in Chrome, in the Chrome ecosystem. And then there's also custom allocators. So, for example, Exim, it's a mail transfer agent that uses its own custom allocator in the ecosystem. It's a lot more rare that you'll see a custom allocator implemented in a code base, but it does happen. Other than custom allocators, you do often see wrappers around malloc just to kind of guide the process in terms of how they're going to be allocating memory. But underneath those, they're typically using malloc and free and whatnot. Why would you do this? Why would you build your own allocator? So mainly for interest and for vulnerability research or binary exploitation. If you're trying to get into those fields, modern implementations are extremely complex. They've got years and years of optimizations, mitigations, corner cases. They're really difficult to fully understand. So by building your own, you can kind of break it down to basics and understand what the allocator is really trying to do. Also, understanding how features are implemented in one allocator can kind of lead you into a direction of where problems might exist in others. Like I said, there's custom allocators that are in place. Most likely, people are going to make the same mistakes when implementing those allocators. They're going to have very similar vulnerabilities and similar bug classes. And then historical context can yield results. So for example, there's a researcher, Yanai Livna, I believe he used to work for Checkpoint Research. He was doing some research in 2018 around the glibc malloc implementation. And what he found was there is a flaw that was reported back in 2001 in the first paper on heap exploitation, which was voodoo malloc tricks. So they called it out in 2001. They thought they fixed it in 2002. That vulnerability laid in place until 2018, so that's 17 years of exploitability that existed within that allocator until it was discovered by him and fixed in 2019. So by understanding, the historical context around mitigations and exploits and vulnerabilities within allocators, you can look and see, have they actually been mitigated? Do they still exist? Have they been reintroduced? Just another example regarding historical context. Ian Beer just gave a talk at OffensiveCon about a section of the XNU kernel, which is the kernel that the Apple ecosystem uses. And what he talked about was the auditing that code base linearly, so just reading the code from top to bottom is extremely difficult, even for someone that's a seasoned researcher like him. But understanding the historical context of what that bit of code is actually trying to do, and in our case, what the heap is trying to do, what the allocator is trying to do, can lead to understanding where there might be flaws. And then finally, it's just fun. I enjoy coding. I enjoy breaking the stuff that I code. It'd be a lot of fun to do. All right, so we're going to get a little bit into my implementations. I start out extremely simply with my implementation, and then I get a little bit more complex. So I'm going to talk about 3 different implementations, and I'm going to demonstrate some vulnerabilities that exist in them and show how they could possibly be exploited. So I mentioned earlier that our allocators will be dealing with inline metadata. So what that essentially means is that the metadata about the area of memory that you're allocating is actually directly in line. It's a header that's located directly before the allocated bit of memory. So as we can see, this is our example of a header that describes our chunk, and it's got 4 different fields. The first field is the size. So this field, it just stores the size of the requested area of memory. So this does not include the header in and of itself, so I'll have to do a little bit of calculation around supporting that header as well. There's also this field next. This field is a pointer to the same type of struct you'll see. It's a struct chunk data, which is the same as the struct that embodies it. So that's really just a pointer to the next allocated chunk. And we use these pointers to build a linked list to be able to enumerate through our chunks. And then we've got a free field. So this really just determines whether or not the chunk is in use by the process or it's been freed and can be used later on in the process for another allocation. And finally, we've got a magic field. This is completely arbitrary. It really just helps us when we're looking in memory and we're doing debugging, kind of spot the different fields. Just makes it stand out. This is what it would look like visually. Like I said, our header is directly in line with our usable memory. And as you can see, all of the fields there prior to the usable bit of memory. All right, so malloc is our version of malloc. You can think of it as my malloc. So what happens on our first call to malloc? So if we look at the code on your right here, you'll see that this global base variable is evaluated, and if it's not set, we make a call to rec space, and we check the return value of that, and then we set that global base to that return value of rec space. So essentially, global base will function as the head of our list. So when we start to enumerate through these chunks, we need somewhere to start. That global base is where we start. Since this is our first call to malloc, we have nowhere to start. So that's why it's evaluated and determined if it's null. And if it is null, we build that base, and that's where we can start from. Let's take a look at that rec space function. So you can see here the entire function on the right is fairly simple. It really behaves as a wrapper to the sbreak system call. So that sbreak or sbrk, however you want to refer to it, is a system call which extends the program break of a process. So essentially what that means is the area of memory that has been allotted to your process by the kernel is extended. So when that's increased, you have more memory to work with. We make two calls to that system call. The first one with a value of 0. That essentially returns your position of your program break, so it tells you where it starts. And then we make another one with the actual size of our chunk. And if you could see that second call to sbreak, we do the size, the requested size, as well as the chunk size. So that's just, again, to give you enough space to include the size that you're looking for memory, as well as the header that's going to go before it. We'll do some validation after that. There's an assert to make sure that the value of chunk is equal to rec. And there's also a if statement that checks, that makes sure that -1, which is an error state, isn't returned by that system call. If all is good, we go ahead and we set the fields. So we set the size to our requested size. We set the next field to null because there is going to be no next chunk yet. We set our free field to 0 because it's not free. It's been allocated to the process for use. And then we set our magic field to an arbitrary value. And then after that, we return the chunk. So we actually return the pointer to the chunk for use. All right, so let's take a look at subsequent calls to malloc. So this would be anything after our first call. So they will follow this code path, this else statement here. So you'll see that last pointer is set to our global base. So that will allow us to pass essentially the global base into this find free chunk function and start to enumerate those chunks to find our free chunk. And then we look at the return value of find free chunk, and if it's null, pretty much the same sequence that we went through the last time, where we make a call to rec space. It's going to go out. It's going to increase the program break and allocate more memory to our process. If it returns a non-null value, then we go ahead and we set that free field to 0. We adjust our magic field just to kind of provide an identifier for that, and we return that chunk. All right, so this is what find free chunk. So we're going to go a layer deeper. We're going to look at the internals of find free chunk. So this is where our enumeration happens. So starting at the head of the list, which is that global base variable that we've passed through, find free chunk is going to iterate through our list of allocated chunks. So see here we've got a while loop, essentially. So while current, so current is the value of each chunk pointer as it iterates through this list. So while current is a value, is not null, end is not free, and is not greater than the size that greater than or equal to the size that we've requested, then we go ahead and we iterate through it by setting current to the next value and continuing the loop. As soon as these evaluations in the while loop are met, one of two things would happen. So either at that point, current's going to be null, so we have not found an available chunk for use, and it'll return a null value. Or the current's free value is not set, and the size exists, so those meet the requirements for the allocation that we're looking for, and the free chunk is returned to be allocated. So just another visual here of what it actually looks like when we have some allocated chunks in memory. So exactly the same visual we saw earlier, just with that linked list. So we can see our header values, our memory, and that next field actually goes ahead and it points to the start of the next chunk. And that's how we iterate through. So we look at that next value, we go to the chunk, we evaluate these fields, we look at this next value, we go to the next chunk, evaluate the fields, and so on. All right, so let's put this to use. So we'll make some calls to malloc. So we're going to make 2 calls to it, one for 24 bytes and one for 32 bytes. And then we're going to call memset just to set some values at that memory, 24 bytes for the first one and 32 for the second one. And this is what it's going to look like in memory here. So this is GDB debugger output of memory after those calls have been made. So if we could see, mapped to the same visual that we saw earlier on the right, we've got our size field here, hex 18, that is going to refer to the 24 bytes that we allocated. We could see the next field has got a pointer. If you look at the value of that pointer, you could see that it actually aligns with what we've got here on the left-hand side for where our next chunk starts. So that's actually how it finds and determines where that chunk is in memory. Looks at that field and says, okay, it's at this area of memory. And we see our 42 values, which is the arbitrary value that we wrote there. And then following chunk, we see it's got the hex 20 for the size field, which corresponds to the 32 bytes that we allocated. And you can see that the next field here in yellow on the bottom is all zeros, so that is a null value. There are no more chunks allocated in our linked list, so that helps us determine, yes, this is the end, this is the final chunk in our list. Same thing, we could see our arbitrary values. We can see that free is set to 0, so these are not free, they're being used. And then we could see our arbitrary 43 excuse me, value set in memory. All right, so let's talk a little bit about freeing and reusing chunks. So extremely simple M-free internals here. So we pass one of these chunks to M-free and we evaluate it. If it's a null value or, if it's a null value, then we're returning -1 for an error state. Otherwise, we are going to make a call to this get chunk pointer. So what get chunk pointer does is since malloc returns an area that points to the usable space of our chunk, get chunk pointer actually kind of subtracts the header value or the header size from that. So rather than pointing to that usable memory area, it's going to point to the start of the chunk. So that'll allow us to then set the actual fields properly as we do below here, and we set free to 1. That makes our chunk usable now, so when we iterate back through the list, we can look at that field and say, okay, it's usable, maybe we can, if the size fits, we could return this, otherwise not. And we set our magic field again to hex FFF, arbitrary value, and just return 0. So return 0 on this will be success, return -1 will be a failure. Again here, this is just the while loop. We saw this earlier. This is how we reuse chunks. So just a reminder here that we are evaluating that current free field and that current size field as long as the size is greater than or equal to the size that was requested and the chunk is free, so that free field is set, we will be able to return a chunk. Otherwise, it'll continue to iterate till it finds one. If it doesn't find one, inherently, the next field of the last chunk will be null, so that will be what's returned is null. And then request space will be called to request additional space. Right, so let's get into a little bit of vulnerability and exploitation around this. So very similarly to what we saw earlier, we're just going to make some calls to malloc, and we are going to go ahead and call memset to set values at each of these locations. So This is actually the second chunk, so this would be test 2 and test 3. And we could see our 42 values that we set and our 43 values. And again, we can see our size field, our next field, and our free field. If we make another call to memset, and this time we call memset with a greater value, so we're essentially simulating an overflow here, we could see that that hex 44 value actually extends down into our second chunk. And effectively, right now, it's just overwriting the size field, which doesn't really give us anything useful, but it's just to demonstrate that we can overflow into this chunk and overwrite the actual metadata of the chunk. So we need to build a target, so we have something useful to do with this new information. So it's going to have a couple of functions here, a good print and a bad print, and then we're going to do a little bit of a jump table, function table. So essentially, that table is just an array of pointers to these functions, and then we can call them by referencing one of the elements of that array as if it were a function. So this is the body of our program. When this is run, it will call good print because good print is the first element of that array. So this is what we're going to try to exploit. We're going to try to overwrite and somehow get it to call bad print. So just to get a better idea of how this works, we'll take a little bit of a look at the disassembly of that program, specifically towards the end of the program. So at the top here, we've got a move call, and what that move call is doing is it's actually moving a pointer off of the stack. So that RBP is our base pointer on the stack. And you can see it's hex 30 off of that stack is getting moved into this RDX register. And then we could see 2 lines down that we actually directly call RDX. So if we actually look and disassemble what's at that base pointer minus hex 30, we could see it's got 2 pointers, the one ending in hex 545 and the one ending in hex 555. And then we'll go ahead and disassemble those 2 addresses, and we could see that the top one, 545, is our good print function, and then there's the assembly for it, and then the bottom one is our bad print and the assembly. So essentially with that information, this here is a proof of concept of how we can exploit that. So what we see here is the same logic that we saw earlier with our calls to malloc, our memsets, our memset that overwrites the size field. And then from that size field, we are going to write in this value. So this is just ASCII encoded value of that stack address that we saw earlier, that stack address that actually held our function pointer to good print. Now, it's our stack address minus a certain size. And that certain size is the size of our chunk header. Because the way malloc works is it doesn't return the start of the chunk, it returns the usable memory, which is the start of the chunk, plus the size of that header. So we need to subtract that. That way, when we get malloc or malloc to return a new writable area of memory, it's actually going to return that value of the stack that we're going to overwrite with the bad print function. So you can see again, we call malloc with arbitrary value at this point. It's 24 bytes. Doesn't really matter what it is at this point. And then we copy the function pointer, so the actual area of memory that holds bad print, into that newly requested variable. So essentially what this does effectively is it returns that call to malloc, func_test equals malloc, returns the stack address as your usable memory. So there are no integrity checks to say, hey, when malloc is returning, it has to be from the heap. It's kind of just arbitrary. So we were able to trick it by overwriting the next value in our header to say, okay, the next value that you're going to return is going to be the stack address. So by doing that, we're able to return that stack address, we're able to overwrite it, and then by just making another call to that jump table, that first element, it will execute bad print for us. All right, so I'm going to talk about implementing what are called free lists or bins. So what is a bin? So essentially, a more realistic way of managing memory is through free lists. So rather than keeping track of every single chunk of memory that you've allocated, you really only want to keep track of the chunks of memory that have been freed that you can actually give back. So that's what a free list is. It really allows for more quick and efficient reallocation. So multiple bins are often implemented to deal with allocations that fit certain sizes and size ranges, which we'll see in our implementation later. And typically, free lists are implemented as either singly or doubly linked lists, depending on the functionality of the allocator. So our previous implementation, we saw we were using a singularly linked list. Every next field pointed to the next chunk. That works great if you are not keeping track of the size of the chunks, or if you don't have to do any kind of sorting or anything like that. A doubly linked list is definitely more efficient when you do have to do sorting, because you're able to insert and extract from the middle of the list, which becomes very important. And on the right here is just a visual. This is actually from the glibc heap implementation documentation, and it's how they implement free lists. So you can see they've got multiple kinds. They've got the fastbins, and then they've got a pointer to bins. That fastbins, we could see, is a singular linked list. It only has pointers in one direction, whereas the bins below have pointers in both directions, which make them a doubly linked list. All right. So our implementation in malloc, we've got 8 fastbins, which are implemented as an 8-element array and then 1 sorted bin. So the fastbins handle fixed size allocations of up to 64 bytes. We are going to adjust our implementation so that every allocation below 64 bytes will be rounded up to the nearest multiple of 8. Which you can see here, 816, 24, 32, 40, 48, 56, and 64. Those will be our bin sizes. So if it falls in between any of those, it'll just be rounded up to that size value so it can fit in this fixed size. The sorted bin handles any chunks that are greater than 64 bytes, and it sorts those chunks from smallest to largest when added. So like we said, needs to be implemented as a doubly linked list. In order to do that sorting, it needs to be able to insert and extract from the list. In this implementation also, I did retain an 8-byte alignment for all allocations, including over 64 bytes. While I did not fully implement this, it is seen in things like the glibc allocator, where by having that 8-byte alignment, if you look at the binary values, the last 3 bits of your size field can be used to encode other data. So it's often used to encode whether or not the previous chunks are free for doing things like chunk consolidation. It's also used by the glibc allocator to determine whether or not it's from a main arena or from a subsequent arena, or if it's been allocated through a malloc call versus an memset call, or the mmap call. But yeah, it's just the idea is by leaving those bits unused, we can use them to encode additional information. So in order to support this new implementation, we will make an adjustment to the header. So you'll see we've got the old header on the left-hand side and the new header on the right-hand side. So we're going to do away with our free field and our magic field. Like I said, the bins will only be used to track free chunks, so there's really no need to keep a free field in place. We also need multiple pointers now. So rather than having just a next field, we're going to have a forward and back pointer. So that'll allow us to establish this double A linked list. And we're going to get rid of the magic field as well because it's arbitrary. And when it comes to heap allocation and allocators in general, we're trying to be efficient. We're trying to save space. So it does become important to make your header as small as possible. All right, and in terms of saving space, we're going to have a little bit of an interesting implementation here. So we could see the difference between a freed chunk and an allocated chunk with our new header. So because the forward and back field are really only used by the bins and only used when chunks are free, there's no reason to have them hanging around when a chunk is in use. So our usable memory will actually start exactly where those forward and back pointers start. And that will we'll be able to write over that when we free the chunks, but to save space, we'll be using that area for our usable memory. All right. Let's take a look at the different types of bins that we've implemented here. So fastbins, like I said, they store fixed size allocations, and they therefore do not require sorting. They actually function as a stack data type, so last in, first out. So as chunks are added to our free bin, they're actually added to the header, or to the head of the list, and then the chunk that was already existing in the bin is set to the next field or the forward field. So everything goes on top and then is popped off the top like a stack would be. Sorted bins are implemented as a doubly linked list, and we'll take a look at the functionality of how that's actually implemented and how those are sorted. Right, so let's take a look at mfree. So that's our version of free for fastbin additions. So mfree itself is incredibly simple. It's got this essentially a call to that get chunk pointer to get the start of the chunk from your usable memory, and then it evaluates the size of the chunk. Depending on the size, it will either add it to the fast bin if it's lower than 64 bytes or equal to it, or it'll add it to the sorted bin if it's greater than that. All right, so the logic below here is the actual logic that handles the fastbin additions. So you see here we've actually got a macro fastbin underscore IDX that takes the chunk size. It's just a really simple macro that will take the size that you requested and return the index of your fastbin array. So since it's an array that holds these values, it's 0 to 8, and it takes the size. So for example, you're taking 64 is your size. You divide that by 8, and you subtract it by 1, and that is your index. So what we're doing here is we're evaluating the specific index of our array to see if anything exists there already. So if something does exist, then like I said, we are setting our new chunk to the head of that list, and then setting the next value of our existing chunk to the chunk that existed in that list already. So again, it just stacks it on top and moves the existing chunk down one. If it doesn't exist, then all we do is set the head of our list to the new chunk and then set the forward value to null, indicating nothing else exists in this list. All right, so this is a little bit more involved, but still not overly complex. So this is the mfree implementation for sorted bin additions. So essentially we're going to iterate through that sorted bin, and if an existing chunk with a greater than or equal to, or with a size that's greater than or equal to the chunk that we are inserting, if an existing chunk with a size greater than or equal to our chunk that we're inserting check, thanks, exists, then then it's set to the current list head. If the encountered check passes the previous checks or newly added chunk is set to the head of the list, our newly added chunk is set to the head of the list. And if the size check and the back field is set, then we perform an insertion. So break it down a little bit better than that. So that first if statement there, it looks at the size of the chunk that we're evaluating in our list, and it says, okay, is that greater than or equal to the size of our chunk that we're inserting? If it is, and the back field of that chunk is not set, then we are going to go ahead and say, okay, this goes at the head of our list, therefore we set the new chunks field to back to null. That'll put it at the top of the list and indicate that nothing exists before it. We'll set the forward to the current chunk, so that's the chunk that's being evaluated that's currently at the head of the list. And then we will set the backfield of that chunk as well to our new chunk that we're adding to the bin. So essentially, it inserts it at the top and changes the values of the existing chunk field to be the second chunk in the list. If we look at our second if statement here, if our current size, so if the current size of the chunk that we're iterating through is greater than the one that we're inserting, and the back one is set, so this is going to do an insertion somewhere in the middle of the list. It's going to set our back value of of our new chunk to the last chunk. It's going to set our forward value to the one that we're iterating through, and then it's going to set the iterating chunks back to the new chunk that's going to be inserted. And then finally is this, essentially, if either of these checks fail, it's just inserted at the end of the list. All right. So chunk reuse in malloc. So essentially, our fastbin fastbin corresponding to the size is evaluated for available chunks. So if there is nothing there, it looks only in the fastbin that corresponds with that size. If nothing exists there, then nothing's returned. If something does exist there, it returns an available chunk. If it is a sorted bin, then if it's outside of the range of the fastbins, then we go through the sorted bin reuse function, which was the function that we looked at previously. And if nothing is returned by either the fastbins or the sorted bins, then we make our call to rec space to request additional space from the kernel and build a new allocation. All right, fastbin removal. So this is what happens if we're reusing a fast chunk. So if we're making use of, if we're making an allocation and we look at our fastbin index and something exists there that would fit that allocation, this is the code that's going to actually provide back that chunk for reuse. So essentially, it's going to check our forward pointer of the chunk at the head of the list. If the forward field is not set to null, then assign the value to the head of the list and return the current chunk for reuse. If the forward field is set to null, set the head of the list to null, which will effectively empty the list, and return the current chunk for reuse. All right, sorted bin removal. Again, this is more involved because there's sorting involved, but essentially what we do is we're going to enumerate through our list until a chunk that satisfies the allocation is encountered. If a suitable chunk is found, then we're going to evaluate the forward and back pointers of that chunk to determine where it exists in the list. So if forward and back are not set to null, so if they are set to values, this means that the chunk is somewhere in the middle of the list. If forward and back is, if forward is set and back is set to null, then the chunk we know is at the head of the list. And then if forward is null and back is sent, we can infer that the chunk is at the end of the list. All right, so we'll talk about a good attack against fastbins. So this all relates to how we are handling allocated chunks versus free chunks. So essentially, we want to take advantage of the use after free vulnerability, which is essentially being able to use a variable after it's already been freed, or use an area of memory after it's already been freed, to overwrite that forward pointer. And we want to be able to overwrite it with our target address. So essentially, we're going to allocate two chunks of the same size so that the overwritten forward pointer is eventually returned as a usable chunk. And write the address, again, we're going to use the same target as we did before of our bad print function to the chunk to successfully overwrite the target. That is odd. Sorry, I'm missing slides. Sorry about that. Arena structure. All right, so this is our subsequent implementation. So we're going to implement an arena. Essentially, an arena is a structure used to store the state of a program's heap. So it's going to consist of our bin pointers. So that's going to be a pin pointer to our sorted bins and to our fast bins. It's also going to have this pointer to top, which we'll talk about later. That's going to be our top chunk. We also include a pointer to another arena. So we're only going to be implementing a single arena, but it's fairly common to be able to allocate additional arenas, especially when you're dealing with a multi-threaded application. And that's going to help avoid heap contention. So if you have too many threads trying to access the heap at once, it's going to either become inefficient or extremely insecure. So yeah, let's look at some top chunk allocation. So essentially, when we make a call to malloc with the top chunk implementation, rather than requesting the size that was requested by the user, by the process, from the kernel, we're just going to make a large default size allocation, and we're going to call that our top chunk. So all of our subsequent requests should be split from that top chunk. Sorry about that. Yeah, you know what? My slides are acting up, so I'll do questions now.
I was just going to say, so an attacker's objective would be to overwrite the memory.
Yes.
And essentially, like, what would they be doing? Overwriting what, like a pointer to?
Yeah, so it's really, so when you get into heap exploitation specifically, if you're going after the heap, the functionality of the heap, which is kind of what we talked about here, about how chunks are freed and how they're handed back, and if you're overwriting like that pointer, you're really looking for it to point to, you want it to point to somewhere that is either going to be executed. So we pointed to, you know, an area of the stack that held a function that we knew was going to be executed. So if we could overwrite that, we're going to be able to ensure that our code is executed. But you could also do like data-based attacks. So you can overwrite the memory that exists on the heap that might be, it could hold function pointers, it could hold something. It doesn't necessarily have to take advantage of how the heap functions. It can more overwrite what's in the heap. And you can do a lot with that. I mean, you can overwrite like permissions values or something like that to just kind of do a data-oriented attack, which are a lot harder to detect. But specifically when you're talking about taking advantage of the functionality of the heap, it's typically going to be around function pointers. A big target, which I would have gotten to, is the global offset table. So when you're doing any kind of program, typically you're going to be calling libraries, external libraries. The global offset table is a writable table, or at least in most cases a writable table, that kind of holds placeholders for those dynamic libraries, for the addresses of them. So by overwriting those, you can overwrite things like, say you're making a call to printf or some function that you'd be using commonly, so you could overwrite that. But yeah, that's typically what you're going for, is some kind of function that you know is going to be executed later on in the process.
So is that now like currently damaged? If someone can overwrite that memory, is that not fixable?
So it's more of a runtime of the process. So that could be like, yeah, if your process restarts, it's going to clear out because memory is ephemeral. You know, it's just going to get cleared out. Or if it's a thread, typically nowadays it's going to be more thread-based. So as soon as that thread dies or a new one spun up, it's going to be, you know, that'll be cured, you could say. But yeah, for the runtime of the process, it's essentially overwritten.
And then how does some an attacker like get to this point in order to overwrite do they have to, I mean, let's just say somebody has a phishing email,
Mhm.
so code has to be run. Like
Right.
this person has to be,
Yeah, so essentially, you're going to have to exploit a vulnerability. So I talked about like heap overflows. I talked about use after freeze. These are, you know, memory corruption related vulnerabilities. You would have to find a vulnerability within the piece of software that you're trying to exploit. Let's say that Barracuda one that came out recently was like, the way it evaluated file names that were in zipped or tarred files that were going through email were getting picked up and processed, and they could exploit it through the file name there. So there's got to be some level of input that exploits a vulnerability that triggers something like this. And then this is more of like an after effect. Like now you're doing exploitation. So you're figuring out, now that I've got a vulnerability and I can overwrite part of the heap, what can I do with that? Yeah.
Is this more of a, when you have people trying to intentionally crash an entire system
Mm-hmm.
in order to then run code in a more vulnerable state, is that more a heaping or a heap style attack or a stack style attack, or is it just adding?
It could really be either one. I see there's a lot of stack protections nowadays. It seems like the stack's a lot more difficult to go for because they've got like stack canaries and cookies and things like that, and it's just a little bit more under control. The heap, like I said, is also globally accessible for your process, so it's a little bit more flexible there, and there tends to be a lot going on. It's a lot more complex, so while there are tons of mitigations and you know, security around the heap, it's just a little bit more flexible. And then ideally, you wouldn't want to crash the process at all because you don't want to raise any alarms that your exploit, a really successful exploit will allow the process to continue to run and be unbeknownst of your exploit at all. Any other questions? Yeah. Yeah, all the code's on GitHub. I've also done this talk in a 3-series article, which is on my Medium. Yeah, which is, if you look in the program, all that info's there. Yeah, awesome. Anything else? All right, thank you, everyone.